Hello everyone. In the previous video we have seen that when a current carrying conductor, straight conductor, is placed in a magnetic field, it experiences force, and the value of force was given by BIL sine theta, or in vector notation it is IL cross B. Now we are going to consider a rectangular loop through which current is flowing and it is kept in a magnetic field. So this rectangular loop has 4 length elements. 2 are the lengths and 2 are the breadth, and they will experience force, and because of the combination of the forces, the rectangular coil will experience a torque. So we are going to calculate the expression of torque experienced by a current carrying rectangular coil when it is placed in a magnetic field. So go through the video very properly and see to that there is no doubt which is left out. So here we are going to discuss the torque. We all know that when we consider torque, it is force into the perpendicular distance between the two forces. That is, we are considering a coupling force which is responsible for rotating a body. Torque is nothing but it is the rotating effect of force. Suppose two forces are acting on a body in the opposite direction such that they rotate the body. Then the value of torque will be magnitude of either of the force into the perpendicular distance between them. So that was the basic concept of force that you have studied in the previous class also. So now we are going to discuss that when we consider a rectangular coil, you can see here the rectangular coil PQRS. In this rectangular coil, you can see here the two poles are taken. One is the north pole, another is the south pole. So we have the magnetic field in one particular direction only, whatever may be the direction in which the current is flowing in different parts of the coil, but magnetic field always is in the same direction. As you can see, it is shown by the arrows here. Now let me explain you something. Here you see that the current is flowing from P to Q, then to R to S in a clockwise direction. Okay. Now let me demonstrate something to you so that you can understand it more properly. Suppose I take a rectangular coil like this. This is just a rectangular coil I am considering. Now in this rectangular coil, suppose this is P, Q, R and this is S. Okay. Now if the current is flowing from P to Q to R to S like this, if the current is flowing like this, okay. So if the current is flowing like this, so we can use because there are 4 components or 4 sides of this rectangular coil which actually represents the 4 lengths. So in each of the length element we will have force which will be given by BIL sine theta. And if we have seen in the figure, let me show you here again. We have seen in the figure that in PQ and in RS the magnetic field acts as perpendicular. So we can use the Fleming's left hand rule to find the direction of force acting on them. So again, if I demonstrate to you here, suppose this is P, Q, R and S and the current is flowing from P to Q here. So if we use the Fleming's left hand rule, you can see here, if this is the direction of magnetic field, so the force will be here and the thumb finger shows the direction of force. Now if the current here in this part, you can see here the direction of current is in the downward direction, so magnetic field in this direction, so the thumb will be towards me. Here the direction, you can see here the direction of magnetic field, this is the thumb in your direction, and in this part the thumb comes to my direction. So we have 2 opposite directional force in PQ and RS. PQ it is towards you and RS it is towards me. we can use the concept of this right hand rule, right hand thumb rule for the cross product for this arm and for this arm, and we will see that the two forces, one will be acting in the upward direction and along the same line one will be acting in the downward direction, so they will cancel each other. But the two forces, one in this arm, another in this arm, they will not be cancelling each other. This force will be moving it in the forward direction and this force will be moving it in the backward direction. So this rectangular coil will start rotating, and we can then calculate the value of force, because the force, two perpendicular forces which are acting on it, two opposite forces which are acting on these two arms are responsible to rotate it. So I hope this is very clear to you. So now you see here the two forces in PQ, it is in the inward direction, and RS oppositely in the outward direction. In QR and this PS, we will find that the direction of force, they cancels each other. Here this will be the direction, and in SP this will be the direction of force, so they will be cancelling each other. But force on PQ and RS, they will result in a torque, because of which the rectangular coil will start rotating. So I hope this is clear to you. This was the basic thing which you need to understand. Now we will discuss the mathematical part. So we have taken this PQRS as the rectangular coil. Now in this rectangular coil, you can see I is the current which flows through the rectangular coil, PQRS, and small a and small b are the length of the rectangular coil and breadth of the rectangular coil respectively. Capital A represents the area of the rectangular coil, which is A multiplied by B. And one more term which you need to understand very clearly, which is theta. This theta is the angle between the magnetic field, this is the direction of magnetic field which I am showing by red ink, and the direction of perpendicular to the surface of the rectangular coil. So magnetic field and the perpendicular to the surface of the rectangular coil, it can be considered as area vector of the rectangular coil, because we know area vector is always perpendicular to the surface. So this angle is theta between the magnetic field and the perpendicular to the surface of the rectangular coil. So I hope this is clear to you. Now see, when we consider this rectangular coil, so in this rectangular coil, we will consider one top view of the rectangular coil that I will discuss later on. But first of all, you see here, according to the Fleming's left hand rule, the magnetic, I have already discussed this, the magnetic force on PS and QR, this PS and this QR, they are equal and opposite, and they are collinear, that is, they act along the same axis of the loop. So the resultant of them will be zero, they will be cancelling each other. But the side PQ experiences a normal inward force which is equal to ILB. This you need to understand. Here the value of force is, you know, the formula, it is BIL sine theta. So it is B, I is the current, L is B here, small b, and sine 90 is 1. So it is BIL. So, or we can write IBL, whatever way it is. The same force will be acting on RS also, and they will be equal forces but acting in the opposite direction, and their line of action is also different. You can see here, if I draw the line of action, you can just see here, this is the line of action and this one is the line of action. So they are in different line of action, so they will not be cancelling each other. So here, if they don't cancel each other, So the value of torque is force into perpendicular distance between the two forces. Now to understand the perpendicular distance, let me consider this, demonstrate this again. Suppose we consider this rectangular point. One force is acting in this direction, another force is acting in this direction, because of which this will rotate like this. So if I see the top view, that is, if I see through this, so one force will be acting in this direction, another force will be acting in this direction. So that top view we are taking here, this is the top view which we have considered. You can see QR, this point is Q and this point is R. So we have this rectangular coil which we see here. V is the magnetic field, this is the perpendicular direction, and the angle here is theta, which is the angle between the magnetic field and the perpendicular direction. So here what we will consider now is, suppose we want to find this distance. This is a perpendicular distance between the two forces. So if we produce the line, magnetic field line in this direction, and if we consider this angle to be alpha, so this angle will also be alpha. This angle is 90 degree. So if this is theta, so we can consider that this will be theta, because here the value of theta is 90 minus alpha, and here also if this is alpha, so naturally this angle will be 90 minus alpha, which is theta, because 90 minus alpha is theta we have considered here. So therefore, if this is the condition which we are getting here, so what we can do is, the value of this length is A, which we have considered here from P to R, this length is A. So this length, the perpendicular distance, using the conventional right angle triangle, the value will be A sine theta in terms of this angle theta. So it will be A sine theta. So we'll write force is IBB into the perpendicular distance is A sine theta. So IB A sine theta. So this is the value of torque. If there is n number of turns, then the value of torque will be given by NIBA sine theta. Now, just now we have considered this angle to be alpha. So theta can be written in terms of 90 minus alpha. And if we put 90 minus alpha here, so it is cos alpha. So NIBA cos alpha we can write. Now, you see here, this IA represents the magnetic dipole moment. This small m represents the magnetic dipole moment for the rectangular coil. So n number of turns is there, so the magnetic dipole moment will be NIA. So the value of torque will be represented by, instead of NIA we write MB sine theta, and the torque in terms of vector notation, it can be written as M cross B. If you remember the torque in case of electric dipole placed in a uniform electric field, it was given by P cross E. Here it is M cross B. I hope this is very clear to you. The direction of torque can be calculated by M cross E using the vector cross multiplication. Now some special cases we are discussing here very quickly. If the angle is 0, that means torque will be 0. NIBA sine theta. If theta is 0, so sine 0 is 0. So the torque will be minimum. It is the condition when the plane of the loop is perpendicular to the magnetic field. This is the magnetic field if it is perpendicular to the plane. So if this magnetic field, if it is perpendicular, that is in the direction here, so the angle theta is 0, so there will not be any torque. And if the magnetic field is perpendicular, that is theta is 90 degree, matlab the value of magnetic field or the direction is parallel to the surface, then the angle theta becomes 90 degree and the torque becomes maximum, which is NIBA sine 90, which is 1. So I hope that this is very clear to you, and this is very, very important. So you need to go through it.